We are truly honored to have with us today Dr. Sharanya S., Associate Professor in the Department of Data Science and Business Systems at SRM Institute of Science and Technology. She holds a PhD from SRM IST and brings with us her over 12 years of teaching experience. Dr. Sharanya is actively involved as a faculty advisor and student counselor, also known for her strong communication and mentoring skills. She is currently guiding two research scholars and has published extensively in international conferences, reputed journals, and Scopus indexed book chapters. With such a rich academic and research background, we are excited to hear from her today. I now invite Dr. Sharanya S. to kindly begin the session. Over to you, ma'am.
Thank you so much, ma'am. Thank you for your warm welcome. And am I audible?
Yes, ma'am.
Okay. Okay. Is my screen visible?
Yes, ma'am. Yes.
Yeah.
No,
okay.
Not yet, ma'am. It is just saying that it has started screen sharing. Yes. Now it is visible, ma'am.
Yeah. Okay. Good afternoon for all the participants. And I extend my humble thanks for the organizing committee as well as for the ma'am for a very warm introduction. And okay. So now today I'm here to share my view about the digital twin and the AI integration in electrical infrastructures. So though I hold a PhD in computer science stream, my PhD is totally inclined towards multidisciplinary structures where I have done the predictive maintenance in aircraft turbofan engines and in bearings and things like that. Even I hold a postdoctoral fellowship from European International University and in the same domain. So now I think with no more waiting, we can just move inside the presentation. Okay. So now here, I'm just here to share my views about digital twin and AI integration with a focus to electrical infrastructures. So digital twins and AI integration is now prevalent or has become more common in almost all disciplines. It is not only inclined or it is not only confined towards the engineering, we can even extend to all the domains. All domains are now facing a great transference in their landscapes. It's mainly because of the AI integration only. So now, with that view, we are moving into the session. Okay. So first, let us now know about a very formal definition of a digital twin. Though we will get inside more details, first, this is a very formal definition of digital twins. There are numerous definitions, and this is one among that. A digital twin, it's a digital or virtual replica of any physical object. So the physical object, it need not be an abiotic, it need not be an biotic object or abiotic object, both living, non-living, any kind of infrastructure which is having some functionality can be transferred or can be converted, or it can have a digital twin of itself. So even the processes can be made as a digital twin. So the main purpose when we create a digital twin is we have to know the context in which the digital twin has to be created. So what are we going to twin? Twin is like a replica of something, which is what is existing. So when I mean it as a digital, it means it is going to exist as a virtual thing. So what are we going to mimic? So that's the main point in the digital twin. So a digital twin, it's an exact digital replica of any physical object or a person, system, processes, whatnot, anything. So it does the main purpose behind it is it should have a contextualized digital version. So in what context are we going to create a digital twin of something? So that's more important about the digital twin. So now, just this is an GIF which tells us how a digital twin will be. So you can see it's a motor kind of a physical object that physical object, the features, the characteristics, or at least the outer things of the physical object, it's getting converted into a digital. It's getting all the artifacts of that object is being captured, and a digitalized version is being created. So that's what is the real digital twin. So now, when we are planning for a digital twin, to construct a digital twin, so what are the main parts, or what should be our main focus area? So that we generally call it as components. So first one, it's a physical asset. So what physical asset are we trying to twin, or are we trying to mimic? So that's the first thing. And the second one, it's the digital twin. So the digital twin itself, how are we going to create a digital twin? So that's the second component. And most importantly, the third component, it's the data. So always the data plays a very pivotal role in the construction of any digital twin based architecture. Why, wherever it is, it's the data, it's going to play a very, very huge role. It's going to hold a lion's share in establishing the communication, or in establishing connection between these two twins, that is the physical asset as well as the digital twin. So you can see the data, it's acting like an interface between the physical asset and the digital twin. So any physical asset, the digital twin of the physical asset can be easily converted, and the bridge that is going to connect these two things as the data. So that's the importance of data. So with this definition and things, this picture would give a more clear idea of the thing. So here we have the physical twins. So physical twin is nothing but, twin means you should have two components. One is the physical component, other one is the digital component. So when I tell it as a physical twin, so it's on the physical infrastructure. It can be a building, it can be an aircraft, it can be an electrical infrastructure, or it can even be a human being. So that's the physical asset. And now in the digital twinning, what do? We collect the artifacts or the data, the characteristics, features, whatever we call, that data collection must be done. And that data, we will convert it into using some platform, some software infrastructure. We will be converting a digitalized version of the physical twin or physical object. So that's the digital twin. So the digital twin is the representative model of all the physical objects. So now, why do we go with the digital twin? So these representative models, why do we create it? So when we create a representative model, we have to create data management and data analytics facilities along with the digital twin, because we should have a purpose of creating a digital twin. So from the digital twin, we will be learning something. So that is being managed, or that is being explored by the data management and data analytics. So once we create the digital twin, what is the purpose of it is, we have to take informed decisions using the data, or using the behavior of by learning the behavior of the digital twin. So the information and the decisions of the digital twin will be captured, and the most important thing is, these information and these decisions will be given back to the physical twin to make improvisations. So that's the main point of creating a digital twin. So it's not the loop is complete, the loop is closed here, because it's not only we don't stop with collecting the data. We don't stop with knowing how the things are working. We don't stop with doing the data analytics, but we do focus on making informed decisions. So that informed decision and the knowledge what we get from the digital twin is given back to the physical world. So there lies the success of the digital twin. So now, why do we need digital twins? So first, digital twins are very essential for turning the data into actionable insights, as I have told in the previous slide itself. So just merely having the data, doing the analytics, learning the models behavior, everything is not going to be a great success once that is not getting implemented to the real world. So the digital twins are very, very crucial for turning the data into the actionable intelligence. So to enable smarter decisions, operations, and maintenance of the real world systems. This definition is very generic. It's not that this can be fit. The digital twin can fit into any discipline. So that's the main thing. So now we'll see few application areas where the digital twins are very crucial. So first is for real-time monitoring. So for tracking the voltage, load, and other health parameters of any electrical, any mechanical equipment. So that is the real-time monitoring. It can be done using the digital twin. And the second very important application is the predictive maintenance. So for one example is prevent the transformer and cable failures proactively. So there are a lot of maintenance strategies we follow. So the maintenance strategies are preventive maintenance is there, proactive maintenance, reactive maintenance, and now we are in the era of predictive maintenance. So when we go with the predictive maintenance, obviously we need the integration of AI. So with the current data and with the current by monitoring the current parameters and by using the analytics and the AI models like machine learning, deep learning models, we will be predicting when this particular machine will fail. So that's the main point in predictive maintenance. Once the failure is known or the time of failure is known, then we can adopt predictive maintenance strategies so that we prevent the failure. So that is possible using the digital twinning. Next is virtual testing and simulations. So testing upgrades or faults safely in a digital environment. So likely, just imagine a scenario where we have a greater vision of creating a new infrastructure. So we cannot go to the ground and directly build the infrastructure and test there because it's very it's not cost effective and it's also not safe. So in that case, we can go for testing the same infrastructure by creating a virtual model of it, and we can simulate all the fault cases or all the cases, whatever we want to examine. So that's the virtual testing and simulation. So that's possible using the digital twins. Next is system optimization. So system optimization, when we do any optimization technique inside the system, so obviously, for example, to improve the power flow, reduce the loss, anything. So when we want to make any small optimization into the system, that can be, its effect can be greatly studied or clearly studied using the virtual twins or the digital twins. Next is smart grid enablement. So grid, in constructing an electrical grid, it's a very extensive operation. And nowadays we are moving towards the smart grids. So smart grids for automation and intelligent energy management. So smart grids are mainly for efficient energy management, energy distribution. That's the main reason why we go for smart grids. But immediately we cannot deploy a physical smart grid. So it's always good to create a virtual replica of it, and we can visualize or we can at least envision how the things are working in the smart grid. So that's one of the potential applications. And the next very important thing is AI-driven decision making. So we can, when we create a digital twin, obviously, whenever we create something as digital, the lots and lots of data will get generated. So how are we going to deal with the data? So AI-driven decision making is one of the pioneering case or use case for creating the digital twins. So we can, what not we cannot do with the data. So the data is actually the king, which is going to drive the entire world, which is actually driving the entire world now. So the AI is completely based on the data. So when we have lot of data from the virtual twin, we can leverage that data for doing forecasting, fault detection, controls, or even for optimization purposes. We can very well do it. So these are some of the areas in which digital twins are very effective, or it is implemented in the electrical infrastructures. So now, going for the evolution of digital twin. So when we talk about the evolution of digital twin, there are 4 categories in which the digital twins have evolved. So the four things, on the basis of 4 criteria, we are going to cover the evolution. So the first is the definition, technology, scale, and the coverage. So the digital twin is still evolving. We are actually in the mid stage. We don't have very complex digital twins. We have very few only, that too at a very small scale. So initially, how did the digital twin started was we have statically updated simulation models. So many of us will have the confusion when what we call it as a digital twin. Is it not the simulation? So what is the difference between the digital twin and simulation? Yeah, we'll deal it in the later slides. So we have the statically updated simulation model, and from there we move towards a dynamic representation where we have the bidirectional flow of data. That is, the digital twin will be communicating with the physical asset as well as the physical asset with the digital twin. All the vice versa communication is possible. And with the integration of all those things, we just formulated a hybrid definition where we are going to bring all the physical entities to convert it into a digital twin. So that's how the definition works. And next, coming to the technology, earlier the groundwork was done using just simple PLM systems and simple simulation tools and platforms. Then these simulation tools were being integrated inside the cloud and edge computing platforms, and later more and more technologies came into the existence or came to help the digital twins, like mixed reality, augmented reality, virtual reality, and a lot of self-adaptive computations, AI models, of course. With all of these only, we are now in a advanced technological era where we can create very high-end digital twins. Then coming for the coverage. So coverage means in what are all the scales the digital twins can be used. So initially, the usage of digital twins, though the name was not actually meant as digital twin, it had a very different name. So it is done in the R&D departments, especially in the aerospace industry. So aerospace industry is one of the industry which is using more of digital twin systems. The reason is we know that an aircraft, when we build it, we cannot build the physical aircraft and allow it to fly. You have to have a digital replica of it, and we have to analyze so many parameters, the constructions, its health monitoring, everything has to be done. So the digital twins are very prominent, or it is finding its place in aerospace industries, especially the construction and the testing of aircrafts. So later it moved into creation of digital twin products, services, and the processes, and all both in the greenfield as well as in the brownfield scenarios. That's a very, very important thing to be noted. So it's not only with the assets what we are trying to construct from the scratch. It can even be implemented over the things which are already existing. So both of the things are supported by the digital twin. And later it had a different life cycle where we plan, build, operate, maintain, everything is possible using the digital twin. So nowadays, the coverage, it has an extensive coverage. Almost all the things can be mimicked. So that's the coverage part of the digital twin. Next, coming to the scalability. So scalability, it is like initially we had only few systems or linked with the digital twin. Now, with the wider technological ecosystems, everything gets connected. So the scalability, it has reached its peak point. So now also the digital twin is still evolving. We do have some extended applications in the later stage. So now we have a $1 million question. That is, I'm talking about digital twin. Is it same as simulation? So now, no, it's different. That we know, but we should have a reason. So now simulations are a way to tell what could happen. So you have an equipment and you can just tell how the thing will work. And on the other hand, digital twin will even tell you what is happening and what will happen. So it is like an foreseeing. The simulation is like, okay, this is how it should work. But in digital twin, we can really see how is it working and how will it work. So that's why the digital twins are more powerful than the simulations. Lot of differences are there between the simulations and digital. I listed only some four under the four criteria. So the first one is data source, which is very important. Simulation relies on predefined data, conditions, and assumptions, and everything will be static in case of simulations. So we cannot change anything dynamically, and we cannot see how is it going to work. So even if we are going to check with that, you will be allowed to do with only limited settings. So there you have a severe constraint in the simulation. But in digital twin, you can use the real-time data from the physical system, and constant updation, reflection, everything is possible because digital twins always comes with the building of AI models. Next, the target. And the simulation means it's only for a specific target. It's so confined. It's ideal for short-term analysis or just training purpose. But if you really want to know the real operation of a particular system in under all scenarios, all conditions, then it's better to go for digital twin because it has a long-term usage, and even in extreme conditions, we can go with the monitoring, optimization, and all kinds of data. Next comes the cost and complexity. The simulation cost will be, obviously it will be low, and the complexity is also, it's less expensive. It's not a very big thing, and simulation is one-time building. So once you build a simulation system, we just use it. But in case of digital twin, it's more complex and expensive because it has to be dynamically updated. Every time a change occurs, then the digital twin, some updation will happen in the digital twin. So obviously, it is very complex, sophisticated, and it's not cost effective. But the cost, it's for the higher benefits it gives. And life cycle, it's a short term. Simulations are short term, and the digital twin is always focused on long term. So it's not bad, or it's not it's worthy to invest in the digital twins. And this is one picture which gives the technologies that are used in digital twins. Wherever we go, we have a creation of digital twin. We do it with the help of the technologies only. So now this is a physical entity, the data is a linkage for it, and the virtual replication. So now the digital twins are going to create a bridge between the real world and the simulation environment. So now when you see the data flow diagram, so from the physical world, the data enters the virtual world, and from the virtual world also, we have the data gets inside the physical entity. So this is two-way communication is the real power of the digital twins. So you can see lot of technologies in the context of AI and computing technologies. Most of them are computing technologies only. So all of these things are used in the digital twins. So cloud computing, reverse engineering, AR, VR, 3D printing, and even the simulation systems, AI, big data, data mining, visualizations, big data, machine learning, so whatnot, all the technologies are getting mapped into the digital twin. So when we are to construct a digital twin, we have to take the help of all these technologies, or most of these technologies based upon the use case. So these are some of the prominent technologies which are used in the digital twins. So now, AI and digital twins building predictive intelligence for electrical assets. So now this is a very, very powerful combo. So because we are going to transfer the virtual replicas into active and intelligent agents. So now when we see the physical product and the digital twins are there. So the physical product's data will be given to the digital twin, or the construction of the digital twin happens based upon the data. And what is the digital twin giving us? Parameters. So whatever the parameters are there, that is being given to the physical product, and the parameters can be again changed. So now here we have a sensor which is going to act like a bridge to convert the physical parameters into a digital form. So that's the sensor. And here what you have is the AI, which is sitting at the back of digital twin, which is going to analyze the data, and with the data, it is going to give us the predictions and insights from it. So this is the combo of digital twin. Now, when you go for the digital twin, it's again, we have the sensor. The sensor will be capturing the data, and you definitely have to curate the data, because the data will be available in a very raw form. You have to do data curation, feature engineering, and then we have on the real data, which is the predictive data, and with lot of critical parameters in it. So now with that, we have to perform the data analytics, and once the data analytics is ready, the insights of the data analytics will be translated into an actionable form. So to the and given to the operating system. So this is how the life cycle of a digital twin goes on. So from the real world scenario, we get the sensor data, and the translatable action insights will be given back to the physical system. So now this is actually the definition what we were seeing. So now why, or what is the capability of the digital twin? So now we have few questions to answer. What if we are planning to build a very remote system or a very intricate system, and where it's not possible for us to retrieve the physical data, physical operational data? And next, what if we have to assess the impact of future or unexpected events? So violating the safety and integrity of the systems. So that's the second question. Or what if we want to analyze or study how the system will behave if we push the system beyond its boundaries, beyond the safety limits? What will happen? So all these three questions, the answer is only one, but we cannot do it in real time. The physical infrastructure, we cannot do everything in physical world because these will cause a greater disaster. So the answer for everything, it is the data. So the data is going to play a key role here. So first, the when you create a digital twin, we get more than enough data. So by analyzing the more than enough data, we can easily get predictive insights. Next, this predictive data, it's not a mere data like a watch data or a time related data, just an image. No, it's not such a kind of data. It's a predictive data which combines a sensor input with a simulation. So now, when you get the sensor input, it means the real-time physical operation of the machine is getting into the play. Next, this enables decision making in even in unmeasurable or in inaccessible condition. That's very important because when you want to have an data from a highly dangerous site, you cannot deploy a human there. So obviously you can have digital twinning of it and you can do it. And now they do go beyond simulations. Digital twin is not exactly the simulation. They give predictive touch to the date, to the operation. Next is, it involves multidisciplinary simulation, generating intelligent reports, and the data analytics. So this is what we have, what we need to plan the future. So when we have to build a futuristic design, definitely we do want to know what is the drawback of the current design. So for that, digital twins are an excellent platform for it. So now we cannot tell whatever we conceive as digital twin is a digital twin. So that is a question that we should ask for among ourselves. So there are various levels of digital twin. So the first is digital model. So digital model means you have a physical object. The physical representation of that object is present as a digital object. So you can see once prompted only, that is through manual operation only, these two things will communicate. Next comes the digital shadow. So this is the next higher level of the digital model. So where the physical objects, artifacts are being embedded or it's being propagated to the digital object, but the vice versa, it's not possible. It's not automatically happening. But in a real digital twin, the physical object as well as the digital object, they do a two-way communication. So the data, whenever it's necessary or in a very frequent manner, both of them do the communication. So that's the level of the digital twin. So now you can see there is no automatic exchange, and a more common example will be plans for buildings. A building plan, it's nothing but you create whenever plan for a building, we have a plan, and we have a physical plan. That's a blueprint of the building. So that blueprint, the building will be exactly constructed like that. But I don't think there is no communication between the building and the plan. And next comes the smart energy meter, which is a digital shadow. So in the smart energy meter, we clearly know that some physical phenomena is captured and it is being monitored. But is the smart energy meter giving something back to the physical world? No, it just depicts what is happening there. So that's a digital shadow. And the digital twin, it's nothing but a wind turbine simulation. So when the wind turbine is acting there, it simulated things is being presented in a virtual environment. So there you can see, you can even change the parameters. Its direction, wind, blade direction, or any other parameter adjustment can be done here. So that will be clearly mimicked or it will be replicated to the physical asset. So that is what we mean it as a digital twin. So next is coming with the types of digital twins. So product twins, process twins, system twins. So these are all three types of twins. And the product twins is nothing but a small product can be created, a digital twin of the product can be created. Process means we can, it's very common in supply chain management, where every time we can learn how the things are moving in the pipeline. So those are all the process twins. And the system twins, it's more complex because it do involve the integration of product and process twins, and based on some timeline factors, it's actually complex twin, and you have to have a clear understanding of the ecosystem in which you are going to create the digital twin. So for example, creating smart factories production line are some of the things. So now, electrical digital twin is just a replacement. So wherever you have a digital twin, in electrical digital twin means we are going to create a replica of electrical system. So the electrical system, we have live sensor data, simulations, and obviously the AI to optimize the faults and permissions. So this is the electrical digital twin. So the common components in electrical digital twin, the first thing is IoT sensors. So IoT's role in creating digital twin cannot be undermined. So AI, IoT, and the electrical assets, all three will be acting together to create a complete environment. So the IoT sensors are mainly used for capturing real-time current, voltage, temperature, anything, real-time physical phenomenon. So that's being captured by the IoT sensors. And next comes our AI models. So the AI models will be learning the data, or the data from the IoT sensor will be sent to the AI models. And this AI model will do one extensive analysis for predicting the failures, or for optimizing what is the best value for this particular parameter, and any such things, whatever we need, the AI model can do it, provided we supply the data right. Next comes our simulation engines. So this is also a part of the digital twin, electrical digital twin. So now here simulation engine, we have to model the dynamic behavioral changes under of the machine, of the equipment. So whenever you are going to change something in the machine, its behavior, its working should be visualized to the simulation engine. So that's the very important phase of an electrical digital twin. And later, this is an optional thing. If you are going for building an highly scalable electrical digital twin, and definitely you have to take the help of edge computing and cloud computing platforms. So this is for enabling remote access, control, and decision making. The data will be transferred to the cloud so that it's available wherever it is procured. So these are all very, very important components in the electrical digital twin. So in the electrical engineering, we will create a digital twin of any system for mainly for real-time monitoring, predictive maintenance, and performance optimization. So these are all the three important use cases for creating digital twins in electrical systems. So here you can see this is just the sensors or the hardware, the real physical things, and you have the software. And again, always I've told you that the bridge that is going to connect these two things is the data. So how you're accessing the data, creating the data, that's the middle. That's the bridge. So now, what are the various layers, or what are all the various things that we need for creating an electrical digital twin? So the first is the physical system. So the physical system, it's the real world equipment, any equipment we can take. So whatever we want to create a model, so that will be the physical system. And next comes our sensors and IoT devices. So these devices are very crucial, because the choice of these devices, it completely depends upon the application. So if you want to monitor a different character, if you want to monitor voltage, then you should choose a particular IoT sensor. Or if you want to monitor vibration, then you have to go for accelerometers. So a lot of other, depending on the component, you have to physical component you're going to monitor, then that particular sensor has to be chosen. Next comes the data acquisition phase. So definitely the sensors are going to pour in lot of data. So you should have a clear-cut platform like SCADA, PLCs, PMUs for collecting all the data in a more presentable or in an accessible format. So that's the data acquisition phase. Once the data acquisition is over, we have to create a digital model. So here I want to mention a few things. Digital model, it's not only the AI. So lot of models are there. Since AI models are easy and it's more robust and versatile, we are going with the AI models. But you do have mathematical models and other simulation models are also there. So MATLAB, ANSYS, Simulink, these are all few very commonly used platforms where we have digital models. But the main difference between these two things is they are not dynamically adaptable. So that's why AI model is becoming more popular in case of digital twinning. And next, once your model is ready, the model will be recreating how the physical asset is going to work. So once the model is going to recreate that thing, it will be generating again loads and loads of data. So that data, using proper analytics and AI procedures, we can definitely detect faults, predict the failures, optimizes load distribution, find optimal value for the parameters, and whatnot. Everything can be found using the AI and the analytics. So this analytics will be giving you recommendations or the insights of what you have learned from that particular system, or what the AI has learned from the data that is being provided from the physical system. So once that is known, next phase, it's the connecting the final connection between the physical system or the virtual system and the physical system. It's the loop closing procedure. So what is the loop closing part of the loop? It's the control and actuation. So based upon the insights, the knowledge that we get from the AI and analytics, we will be adjusting the settings, or for example, inverter frequency related to anything. So based upon the insights, we can make adjustments in the physical system and prevent the failure, or prevent the unfavorable things to happen, or we can do the control over the thing, control over its operation. So that's the main part. And another thing is, you can have visualizations. So visualization is a very effective form of human machine interaction. So the visualizations will clearly tell how the data is proceeding. So that's also a part of the digital twin. We can create dashboards of all the physical processes that's happening using the data that we get it. And also the AI analytics can also be visualized. So visualization will be fitting inside both physical system as well as on the virtual system. So these are all the various layers in which we have to build the electrical digital twin. So now components, again coming for components. So first is, it's a more clear view of what we have seen as an gist. So the first one is the physical layer. So here comes our real world electrical system. Any system you can take, all the systems will be lying in the physical layer, which is our physical infrastructure. Next, the physical infrastructure will be producing, or the operation of the physical infrastructure will be monitored, or it will be known to the system using the various sensors. Smart meters, relays, lot of things are there. Here I have given only few important things, smart meters, and these are all some of the things which will be measuring the working condition of your physical system. So these, actually they are converting the physical phenomena into a digitalized version. So after this, we'll be having only the numbers and the data. So now onwards, we have to start working on the data. That's the second layer. So now the second layer, once you have the raw data, it's the data acquisition and edge computing. So as I told, SCADA, Raspberry Pi, some industrial gateways and PMUs, PLMs, all of them are used for data acquisition. And edge computing is an optional part of it. So where instead of offloading everything to a cloud, you can definitely have an edge server inside the premises itself, so that you can have the decisions taken inside the campus, inside the premises. So that's what edge computing is going to facilitate. So that also comes under the layer 2. And next comes the layer 3, where you have the cloud or the data processing layer. So the cloud layer, so you can offload the data to a cloud server where all the processing can be done. So what is the main purpose is, we can have or store historical data. So for example, this InfluxDB is a very famous time series data, and we can get that data for doing the AI simulations and for creating AI models. So lots of data will be pouring from the system. So we need an infrastructure to store the data. So that could be a cloud platform. So you can have the infrastructure as service, and you can save lot of data in the cloud. And next, we can do power quality analysis like harmonics, voltage signs, everything can be done in the data processing layer. So you have the data processing can also be done at the cloud. Next is, you can integrate with the current energy management system. So that energy management system of the particular area, the particular site can be benefited by getting that data, and the insights of the data can be given with this EMS. And next comes the digital model and the simulation. So the digital model can be created using the AI, artificial intelligence, or even mathematical models can also be created. So MATLAB and We can create the digital models using the and ETAP, PS CAD, power system CAD, and ANSYS Twin Builder. So these are some of the digital twin systems that is already available. And what is the end request or end result of building a digital model and simulation is first is to do the predictive maintenance. So when is this particular component going to fail? Or is it working under a good condition? What is the health status of this particular equipment? Next comes the anomaly detection. So is there anything anomalous is going to happen? That is anything which is not normal is happening there. So that can easily be picked using this digital model. And next is transmission, power transmission. So how is the power transmission currently happening? Is the demand and the supply is being rightly matched? So those are all the things that we can learn from this digital model. So this is done using the AI and the predictive analytics. So the data, the digital model will be giving a data, and this is what we are going to do with the AI. So these are all the high-end solutions or the high-end formulation, which will help us to build the futuristic things. Next comes the data control and actuation. So here we know that once the data is given, once the models are being trained, everything is okay. We will be trying to control it. So we'll have a control over the existing systems. We'll have we'll adjust the things based upon the insights provided from the AI data. And next comes the visualization layer. So we'll have the real-time dashboards or even the fault location systems. So these will definitely help the operator to know what is being or what we are going to adjust. So that's it's a visualization. Visualization will help us to understand things better. So now we will be seeing few use cases of the DTs. So first, the flow of this particular thing goes through this way, you can see. So this is the digital twin definition. So how are we going to create a digital twin definition? Digital shadows can be there. So shadows are nothing but like a smart energy meter where only one-way communication is happening, or a virtual representation of a thing. These are all various options available. So bidirectional communication, physical asset and services data, everything. So when you combine virtual representation, bidirectional communication and the physical asset, you call that to be a three-element definition. And when you combine it with servers and data, it becomes the 5-element definition. So these are all the various DT definitions. So now, once those definitions are done, we can visualize these things, extended DT definitions. This is what we are going to visualize, or we'll be just focusing on one particular thing. We will be narrowing down. And next, we are going for the potential application part of it. So what is the application part of it? So you can see condition monitoring can be done, remote monitoring can be done. So it can be done even for the grid plant or a single unit or for a complete system or a complete ecosystem. Anything can be done. So depending upon the use case, we'll be choosing between remote monitoring or the on-premise condition monitoring. So this is the few application. And then we have a framework. Lot of frameworks will be there for the digital twins. Frameworks are nothing but the models, AI models. So based upon the models, we'll communicate to the potential application part also. And what happens here in the framework is that whatever the technology, whatever the data that we gather there, it is the data acquisition, modeling, analysis. Lot of things will be done in the enabling technologies. So this data will be processed, and the end results of this data processing will be leading to the maturity of the next generation digital twin. So now you can just you can tick the check boxes. Are we considering the live data or multiple case scenarios considered? Is it a very generic framework or a specific one? So how are we going to build a digital twin? So this is how the digital twin has to be validated. So now we'll see few example digital twins. So the first one is it's just a case study only. So a lot of other forms of digital twins is also possible. Energy management using digital. So here you can see the digital twin actually presented here in this particular slide. It is it models the energy consumption of any building. So here, what is the primary focus is you have to identify what are all the potential opportunities for energy savings and improve the energy management by monitoring the physical asset performance. And then we identify the by problems. What are the things which is going for or data energy leakage, anything. So that has to be identified. And this is a one comprehensive use case where you have to do maintenance part, you have to go for optimization, and you have to go for data gathering, everything. So here, ultimately, we have to reduce the energy consumption without by improving the energy efficiency. So here you can see this is the contemporary framework where you get the data and you have the simulations and where we have the horizontal and the vertical integration of things. And the sensor data, we will be giving it to the next higher level where we have the data insights. Here the AI models will be operating on. So it's actually a two-way communication. So between there, we'll get back the data so that we have all the changes being done in the energy management system. So this is the energy conservation system for a particular building. So now, how does it work? Whatever I told there, it's being elaborated here. So first we have the IoT sensors, which will be monitoring the electrical usage, temperature, the health status of the equipment, and everything, environmental condition also. Next, the sensor data plus the historical data. Already we will be having the backup data. So that data plus the sensor data along with external inputs plus the engineering models. So the models, it can be AI models or even the mathematical models. So those models will be giving us three flavors of services. One is the visualization. So how is the energy consumption pattern going on, and the load pattern, everything can be visualized. So that's one way of digital twinning. Next is simulation. So simulate what will happen if this is going to currently, if this is going to persist for 1 more hour, 1 more day. So in that case, we can go for energy demand. Okay, what will be the tomorrow's energy demand? That forecasting can also be done. And next comes optimization. So the optimization means load shifting, and you're going to you can just shift the load between the various control centers, and we can adopt predictive maintenance and everything. So now the data or the insights, what we do, it is again becoming a usage habits, and this is going to give a continuous improvement over the physical systems. So this is the complete workflow of the digital twin. Now, when we go for the digital twin for any predictive maintenance, here it's given as a wind turbine. So you can see this is the physical equipment, and now this is a digital twin model of the physical equipment. So this is being constructed using all the asset data, real-time data, context data, every data. So now in the digital twin, what we do is we will be collecting all these data. Once the data is being collected, we now with the data, it's actually rich. It has a lot of knowledge in it. So with the domain expertise, with the historical data, and with the AI models, we will be able to draw insights. And next, parallelly, we will be getting the analytics. So analytics is nothing but how the particular the patterns of the data can be easily visualized. So that's the analytics part of it. So this is one of the digital twin for the predictive maintenance part. So now, how do we know when there is a failure? So obviously, in the knowledge part or even in the analytics part, we can very well find what is the failure part, or what is the abnormal thing that is happening inside the wind turbine. So when that abnormality is sensed, so we can easily find, okay, a failure is going to happen. Next, IoT based using digital twins. IoT based systems, this is a power transmission system. We can see you have a power plant and the power is going to reach a home location. So you have lot of entities in between, like step-up transformer, high voltage transmission lines, and a substation. And again, from the substation, it has to reach out. So at every possible point, we will be monitoring or certain parameters. So using this IoT, and also from the cloud also, we'll get the control. So now you can see here monitoring parameters are what is the dissolved gas, temperature, partial discharge, lot of things are there. Everywhere we will be monitoring the parameters. So these are done using the IoT sensor. And here we can see the values are sent to the IoT cloud, and the possible decisions what comes from the IoT cloud is the most important thing. Here you can see continue the normal operation, or carry out the maintenance plan, or carry out the outage plan. What is the lifetime? How long this will continue? So likewise, you can just get the values. So here you can see in the high transmission voltage lines. So you can see what is the decisions, adaptive protection setting, dynamic line ratings, and carry out the breakdown prediction. Because if there is some problem, you can see if the parameters is gas leakage, on and off cycles, you can see, then you have to carry out the maintenance. So based upon these things only, the decision systems will give it insights. So now, when we go for this, is very, very common and it's a need of the hour, photovoltaic panels. So here you can see we need three things. One is the digital twin to estimate the output characteristics. So the output characteristics of a photovoltaic panel is very important for estimating the faults there. And next is residual vector. And residual, by when we mean it as a residual, it's nothing but the measured difference between measured value and the estimated value. So that's the residual vector. And next, the evaluation part. What is the difference and how long can we permit this difference? So that's the evaluation part. So this is the PV fault diagnosis system using the digital. So now, as a last part of my presentation, I would like to introduce some few digital twins already available in the market. First is Azure Digital Twins. It's being developed by Microsoft. It's completely based on cloud and it's for building smart buildings, factories, energy grids, etc. So now, the features of it is it has a spatial intelligent graph where we can do the space planning. So based upon the space, we can place our infrastructure, and that space planning can happen in this Azure. Next is digital twin object models. Even a small object can be modeled, and the computation is also provided. And one provision is that data isolation using multiple and the nested tenancy capability. So you can have multi-level data isolation. So it's not that all data will be available for all people. So you can have access restrictions there. And very importantly, it is being integrated with Microsoft services. So Azure digital twins are very popular. This is one of the screenshots where the spatial planning of the system, digital twin system. And next comes the Siemens Accelerator. It's being developed a part of the Siemens portfolio, and it's mainly used for manufacturing plant, industrial equipment, and energy system. So now the next one is GE Digital Predicts. So it's also Predicts platform. It's mainly focused. The GE is it's called a general equipment, and this is mainly for electrical engineering, power generation, wind turbines, grid optimization. All these things can be done. And now we'll dwell more inside GE because this is so context specific. So now the GE systems are being developed, or it has an integrated Humble AI. So Humble AI, what is the specialty of Humble AI is it will be fallback, it will make your physical asset to go back to the safe operating condition. So that is why Humble AI is very, very important, because as GE Digital Twin is mainly for electrical infrastructure, it can convert the electrical infrastructure to move to the safe zone. So the last one is design considerations or the challenges in the digital twins. So the first one is data related challenges. So we have lot of data. So when we generate the data, if the data is too noisy and and we know that the data integration, we are getting the data from heterogeneous sources and the sensitive grid operational data, all of these are great big challenges. Again, complaints with the regulations. So any complaints issues, it will vary from region to region. So this is one of the important challenge that we have to combat. Next comes the modeling challenges. So the modeling challenges is, as the electrical system, it's very complex. So you have to model the complex system behavior, and the model validation is a great checkpoint for us. Next one is scalability. So you have to always check the scalability of things. As the electrical infrastructures will be expanding, the scalability is also a bigger problem. And extending digital twins to form components to large networks, it's a very big modeling challenge. Next comes computational technical challenges. Is the digital twin that we are constructing capable of doing real-time processing? And if you're going to adapt to a new technology, is it interoperable? What is the compatibility between them? Next comes the latency and bandwidth. The data transfer has to happen between the physical asset and the digital asset. So what about the latency, bandwidth, and other network considerations? And how is the synchronization happening between the physical and digital twin? So these are all some of the computational challenges. Next, the life cycle challenges. So how well the organization is adapting to the change? and the cost incurred for creating or constructing the digital twin, and the maintenance part of it, and adaptation with the already existing systems. The next very important is cyber security. So now we know that the data is getting flowed in an open environment, especially the wireless environment. Always we have a chance for the data to get tapped, and any cyber attack happening on this will be collapsing the entire system. So cyber security challenge is a very important thing that we have to immediately address. Next is, there is, as of now, there is no lack of standards and the compliance with the industry regulations. So whatever we create, we don't have any validating things for the digital twins. So these are all the design considerations. Whatever I presented here, it is going to give you one overview of how the digital twins work, and this can be adapted for any engineering discipline. Here I have presented with the context of electrical infrastructures, and lot of scope for research is there within the electrical infrastructure, especially the cyber security challenges and the data challenges. So these are all two important things where we can focus more